Hey guys, welcome to Varmus Chem and welcome to the thermochemistry behind heating water. This video is going to be about the heating curve of water, and it's going to be water at sea level or 1 atmosphere pressure. So let's get started. In this video I'm going to be using what looks like perhaps a graph akin to a graph. If you don't happen to have it, you're watching on the internet from somewhere, or you're one of my students but don't have a hard copy of the sheet, pause it and draw it out. It'll really help you. Here we go. So we're going to be studying the heating curve for water at 1 atmosphere pressure. That's what this entire diagram is about. We're going to be writing a bunch of stuff on it. Let me describe this diagram for you. On the y-axis, if you will, we have temperature. We're going from minus 30 degrees Celsius all the way up to 140 degrees Celsius. On the x-axis, we've got heat being added. And this is the graph that will tell our story right here, this line with all of these corners. This represents the addition of heat. This is going to represent the subtraction of heat or the removal of heat. Also listed over here for your benefit are the constants for water. Let me first talk about that briefly. The specific heat capacity of water is 4.18 joules per gram degree Celsius. But notice, water that is solid ice, depending on the state, therefore, has a different specific heat capacity. And the same is true with steam. So these three values are specific heat capacities for H2O. They vary depending on the state of matter. So the solid phase, which is ice, would be 2.09. When it becomes water, it's 4.18. And then when it becomes steam, it's 2.01 in this region. I also want to draw your attention to the heat of fusion. So this is the amount of heat that is going to be absorbed by ice as it melts. And this is expressed on a per mole basis. So you are going to need to know what a mole is as well and how you calculate a mole. When you go from liquid boiling water to vapor, the heat of vaporization, right here, you got 40.7 kilojoules per mole. Notice these three are in joules. These two values, these two constants, are in kilojoules. These will be given to you on a test, and you just need to use them to interpret data. So this is solid ice, and I'm just going to represent that almost with a bunch of ice cubes, if you will. That is solid ice, and I'm just going to write that over here as solid ice. And that is the solid phase. And this is, so therefore this is water, H2O, S meaning it is solid. In this area, as you add heat, you are going to be changing the temperature. So right in here, we're going to write the formula for enthalpy. Q is equal to mc delta T. That is occurring in this area. Right here, if you notice, that is 0 degrees Celsius. So this is where ice is going to start melting, but not quite here. This entire range right here, notice the temperature stays 0, but we are adding energy because heat is being added right here. The temperature does not change. And the PE stands for potential energy. So this is a change in potential energy right here. That is what this flat line represents. When you're going in this direction, you are melting. When you're going in the reverse, it is freezing. And we're talking about from here to here in this region. When you are expressing the change in temperature, the delta T, and you're measuring enthalpy by Q, here the temperature is changing. So this slope is changing. Now once we get to liquid water over here, I'm going to draw the water molecules as being a little bit further apart. And again, this is not to scale. I'm just drawing water molecules for you to understand that they are not all clumped together. We measure the enthalpy, delta H, in terms of MCAT in this region of the heating curve till we get to this corner. So this is a change in kinetic energy right in this area as well. So I'm going to write that as change in kinetic energy right in here. And that is occurring in this area that has a positive slope. And just remember, in here, this entire region, the specific heat capacity of water is 4.18 joules per gram degree Celsius right in here. And I'm going to represent the change in kinetic energy with a delta KE. And remember, delta PE stands for change in potential energy. And the equation here is Q is equal to MCAT. So in here and here, a change in kinetic energy, in where there is a slope of any kind. Here it's flat. There's only a change in potential energy. The intermolecular forces are being rearranged so that it can become a liquid and is no longer a solid from this point, from this corner on. We're adding heat. So this is going to be, you guys tell me what it's going to be. Come on, you got this. Adding heat to the system, and therefore this is going to be endothermic. So this entire exercise is endothermic as we're headed towards steam in this direction. Right up here, water's going to start boiling. It tapers off again. And I want to draw your attention to a line here. The length of this line, now this entire diagram is not to scale, but notice this length is greater than this length. And that is because in order to go from boiling water to steam, right here is this mark for steam, right here at this corner, water actually has to absorb an enormous amount of energy. So notice the temperature stays right at 100 across the board. So from here to here it's 100, all the way from here to here it's 100. But we have added this much heat. Look at the x-axis. We've gone from here to here on the x-axis. So it's grabbed a lot of heat. And this is vaporization. It's becoming a vapor. It's becoming steam. And in reverse, that is called condensation. So if I asked you to calculate from here to here, you'd be using Q is equal to MCAT. If I asked you to calculate from 0 degrees, but from this corner, you would have to add this amount of potential energy to your Q is equal to MCAT calculation. Up here, water now becomes steam. I'm going to represent the particles with these little arrows. You're flying any which way and where, I guess. Again, I'm not drawing the exact same number of particles, but I just want you to understand that this is a gas here, and this is steam. Okay, and here the steam is getting heated further, and this is going to be represented as H2O gas. Right here, these are water molecules. This is going to be represented as H2O liquid, horrible L, anyway, and these are water molecules. These represent water molecules right here. One more thing, super important. In this region again, there is absolutely no change in temperature. Notice it's at 100. No change in temp. I'd like you to highlight a couple of things. There's no change in temp right in here. And right in here, there is no change in temp as well. Right in here, the molecules are rearranging themselves, but they're absorbing heat, but the temperature is not changing. So this is, again, a change in potential energy. So this is delta PE. That is a change in potential energy. So in this region, you're going to be using the heat of vaporization, and it is from here to here is 40.7 kilojoules. That's a huge amount. That's why steam is so much more dangerous than boiling water. Temperature-wise, it is the same, so it's just absorbed a lot more heat. It started here, look at that, on the x-axis, and it's gone here. So over here, the temperature is again climbing, and up in this region again, it would be Q, right along there, it would be Q is equal to MCAT, again, and that is a change in kinetic energy. So this is going to be delta KE, hoping you can see that. So this entire region is a change in kinetic energy. Why? Because the slope is not 0. Note that the slope here and here are different from the slope over here. This is going to take a lot more energy to crank up the temperature in this region. But nonetheless, you can do it here and here as well. So just to recap, this is called the heating curve for water. If you heat water from minus 20 degrees, let's say up to 130 degrees, you would be adding the value of Q is equal to MCAT in this region. Then when you got to this corner, the temperature would level out, but you'd be calculating the number of moles multiplied by the heat of fusion right here. So you're going to be adding some enthalpy to this, but it's not going to be using the MCAT equation because there is no change in temperature. From this corner all the way up to the point where water starts boiling, this corner, you again use Q is equal to MCAT. So let's say you wanted to measure how much heat went from 0 degrees to 100. Your temperature change would be 100 degrees. So Q is equal to MCAT applies all across here till you get to this corner. Right here, you are going to again have your moles figured out, and you're going to multiply that by the heat of vaporization, which again is 40.7 kilojoules per mole. These numbers, guys, are always given to you. So you go from here to steam, and then again the temperature starts rising, and so now you're superheating the steam, and you're going to use Q is equal to MCAT here. So if you were measuring to 130 degrees from, I think I said minus 20, you would have to add this phase, then you crank it up all the way here, so you'd add Q is equal to MCAT here. Then you're going to multiply your moles times the heat of vaporization. Then again, you're going to be doing the Q is equal to MCAT here. So it's just a series of additions. So you'd be adding it from here to here, second addition, then you've got this whole region, then you've got this right here, and down to minus 20. If you flip this heating curve around, it would be called the cooling curve for water. And just remember, when you remove heat energy, so if you are removing heat energy from this system, so when you remove heat energy, it is an exothermic process. And again, no change in temperature where the lines are flat. So that, ladies and gentlemen, is how you interpret the heating curve of water. It becomes very, very important. So for example, when you have sea ice and you have ice on the poles, they are absorbing vast amounts of energy, even though the temperature doesn't change. But in absorbing that vast amount of energy, it is controlling temperature on Earth. I might make a video on sea ice and its impact on heat a little bit later, but I hope you found this helpful. Bye.